Okay, off we go. So picking up where we left off last time, so we had talked about Gauss's divergence theorem, and we were looking at some physical examples. The first couple of examples that we talked about involved fluids. So this next example certainly doesn't start off about fluids. This next example is about gravitational fields, and for a point mass, this is the formula for a gravitational field right here. We've seen this before. We talked about this back in Chapter 3 when we were first introducing vector fields. So we have a bad news, good news situation here. The bad news is, if you look at this vector field, you will find that it has a denominator that can be 0, and that means that it's undefined. And remember, something we talked about a long time ago is that these theorems that we're talking about, all of these accumulation theorems, as I like to call them, they're all extremely delicate. Everything has to be defined and continuous and differentiable and all the goodies, right? Or else things get weird. And so that's bad, right? We have a singularity here. This vector field fails to be defined at the origin, namely where the mass is. Here's the good news. This vector field, as written, is for the situation where you have a single point mass. And yeah, the good news is that's not physical anyway. So it's just not at all how the physical universe works. There is no such thing as a point mass, right? Mass is always distributed over at least some volume, however little, but there's always some volume. So what we're going to find basically is that this formula is actually okay to work with to approximate everything other than what's happening in a very, very small little region. And I'm going to kind of just kind of dance around what happens, dangerously close to the region. Okay, so and it turns out it's not a problem. It's nothing to worry about. Okay, so here's back to this vector field, our gravitational field, and you look at that, and this might look familiar. This is actually the same exact vector field as for a light bulb. And you can see the picture. We didn't write down the formula previously, but here is the picture that I've drawn of it. You can see inverse square radial. And then you look back at the light bulb picture, and it's literally exactly the same picture. In fact, I copy-pasted to make my drawing easier when I was writing these notes. So exactly the same vector field. So we know tons of stuff about this vector field already. But more to the point, and I've made this observation in the past, when something in the physical world behaves as if something is true, you can pretend that something is true, and it's going to go just fine, right? So I love doing this. I think it's a great little tool. So in fact, then, because this looks just like the vector field where there was a point light source emanating photons, we're going to reinterpret gravity as that a point mass just emits little particles called gravitons. It's like they're little photons, except that instead of communicating light, they communicate gravitational force. Now, is this true? Oh my gosh, I don't know, don't really care. I've talked to physicists about this. You get a very long discussion of, complications, and it's very sophisticated. But it doesn't matter. For our purposes, whether this is physical or not is absolutely not the point. The point is, you can think of it this way, and you will get right answers. And so you might as well pretend that, in fact, this is, how gravity works. So that's what we're going to do here. And let's see here. So that being the idea, let's think about this equation right here. From the point of view of mass, don't think of mass as creating some abstract vector field representing forces. Don't think of it that way at all. Think of mass as kind of like a little light bulb, and mass just shoots out these little particles called gravitons every which way, right? And, mass emits gravitons. the more mass you get, the more gravitons you get. Right? More mass, more gravitons. Let's think about these gravitons. As these gravitons fly around, right? Here's let's say a graviton flying along. Notice that every single graviton that gets created by this mass is going to flow through our surface. Right? So, and by the way, create flux, because that's what a flux is. Flux is a flow of your fluid through your surface. So the nice punchline is mass creates gravitons, gravitons create flux. Right? So this is a really, really powerful point of view, I think, that if you just, again, is it make-believe, is it not make-believe, doesn't matter, right? It's as good as true, and so we might as well think of it that way. Thinking of gravity like this makes for a really easy argument for understanding the relationship between mass inside of a closed surface and the gravitational flux through that surface. It's just, it's, again, the more light bulbs you have on the inside, the more light's going to hit the surface. It's as simple as that. All right, so believe it or not, we are a hop, skip, and a jump now away from a really powerful conclusion. And let's look at this equation right here. Real quick, let's go back to this equation. Don't worry too much about this negative 4 pi g. That's just a constant. That's sort of a reality of the physical world. More mass means more flux. Yeah, sure, but nevertheless, it's a proportionality. Negative 4 pi g just happens to be what that proportionality is. Don't worry about where that comes from. It's the nature of the physical world. So that said, looking at everything in this equation except for the negative 4 pi g, notice all it says is mass is a triple integral of density. So that top line is a freebie. Right? We've been computing mass as a triple integral of density since a month ago or more. It's a long time ago. And then this bottom line down here, this is just the divergence theorem. Right? Gauss's divergence theorem right there. So what we have, again, out of this graviton point of view that gives us this, I think, very physically plausible first interpretation, what we get is that these two integrals are always equal. How could that possibly be? They have different integrands. If the integrands are different, surely where they are different, you would think these integrals would be different. So if the integrals are always equal, that means that the integrands must always be equal. And that gives us this very powerful conclusion right here, that the divergence of the gravitational field is always proportional to mass density. And by the way, this would be really, really hard to prove otherwise if you wanted to sort of brute force this. Imagine now a problem where you have a distribution of mass. Let's think about this table right here, for example. That's not a point source, right? There's mass over here and there's other mass way over here. Each one of these, every particle in this entire table creates its own gravitational field centered in different places. If I were to write down the entire gravitational field created by the entire table, or worse, by an entire planet, right? It's unthinkable. There's so many different vector fields to write down and add up, and they're all centered in different places. It's implausible. And then you ask me what's the divergence of that gravitational field, the total divergence? Oh my gosh, I mean, come on, it's ridiculous. On the other hand, you take this graviton point of view, the divergence, mass density. And a constant that has to be thrown in here for good measure. Really powerful point of view. I'm a big fan. So I would take the point of view that says that since Gauss's divergence theorem was central to making this conclusion work, I would argue that Gauss's divergence theorem really is pretty essential to having a full understanding of how gravity works, right, in a obviously at the surface of the Earth, gravity is pretty simple. It's down, right? That part's easy. But in a non-constant setting, if you're talking about planets and orbits and stuff like that, gravity is a very complicated thing that requires understanding the divergence theorem to be able to capitalize on awesome stuff like this. Okay. All right. Real quick, I'll point out one last thing. Mass creates flux. Constant, sure, okay, fine, right? But mass creates flux, and then likewise, mass density creates flux density, right? Remember, that's one of our interpretations of divergence, is flux density. So, again, really strong connection between what you might call sort of global ideas and then local density ideas. Okay. All right. Now, so you might say you have no interest in becoming an astrophysicist, and you're not going to become an astronomer or an astronaut, and maybe you figure you're going to spend your whole life on the surface of the Earth where gravity is constant, nice and simple and easy to understand. True. But you are probably going to have to deal with electric fields. A lot of y'all are engineers, most y'all are engineers. And electric fields, yet no such option. Electric fields, highly non-constant inside of every piece of electronics, right? You just can't assume the electric field's constant. Here's a beautiful thing. Electric fields, totally different physics. Completely different physics, right? But they too are structurally the same as gravitational fields. They are inverse square radial, just like gravitational fields, just like light bulbs, right? Just to extend the analogy. So everything that we just got through doing with gravitational fields, based on the idea of, hey, look, it's basically particles flowing outward, and then concluding from that, all of that same stuff comes along for the ride, right? And you can view, as it turns out, in the same way you can view mass as creating gravitons, which create flux. Likewise, you can think of charge as creating some little particle of sorts that communicates electric fields, and that creates electric flux. And again, it's just a matter of playing some little detail games to figure out what the proportionality constant. It happens to be that right there. It's a standard physical constant, not our problem in this class. And then you play the same other games. You integrate over a solid, right? And then write down the divergence theorem, and that means that these two integrals are the same, and that means that these two integrands are the same. It's the exact same argument that we just got through going through. Is exactly the same. And we get, again, a really powerful conclusion. And arguably, again, two powerful conclusions. When you have a distribution of charged particles, if you're interested in the total electric flux through a surface that is a closed boundary surface, you just have to count up the total charge inside of that closed boundary surface and fix it with a proportionality constant, and bam, there's your flux. Likewise, if you want to look at the overall electric field, very complicated formulas. If you have multiple charges in various different locations, or worse, a distribution of charges across different locations, computing that electric field is monstrous. It's just impractical. Taking the divergence of a monster is, still some effort in that. Or, again, clever argument, that divergence is always proportional to charge density. So really, really powerful physics conclusions about charge and divergence of the electric field and flux of the electric field, and the thing that connects them, again, is Gauss's divergence theorem. That's doing the real heavy lifting here. Okay. All right. So now, FYI, these results here, this one here is one of Maxwell's equations. This is one of the big deals if you study E&M, which y'all either have or will. If you study E&M, Maxwell's equations, this is what in my personal ordering, my preferred ordering, I would call this Maxwell's first equation. And this is the other version of it. We don't even really call these different equations. We call them different versions of the same equation, right? Because, again, it's kind of all about densities. This is flux density. This is charge density, right? They're not that different. And again, the thing that makes the connection, the thing that allows you to relate these two statements to each other, at a casual glance, these statements look really, really different. But the thing that connects them, Gauss's divergence theorem. Super big deal. Okay. All right. So, nice physics examples. Let me pause real quick. Is everybody okay? All right. Moving along. I'm going to talk about Stokes' theorem now. This is the second big part, you might say, of section 7.3. It's another accumulation theorem. You're going to notice the pattern. We're going to talk about boundaries and orientations. We're going to talk about an accumulating quantity. I'm going to wave my hands and make claims about how psychologically you can just see it in your mind as distributed over the interior, even though you compute it on the boundary. We've been down that road a bunch of times, right? And then we'll declare that there's an appropriate corresponding notion of density, and we'll put it together and write down a theorem, right? So it's structurally just like every one of these theorems we've already seen. And just to enumerate how many times we've been down this road, fundamental theorem of calculus, fundamental theorem of line integrals, Green's theorem, the other version of Green's theorem, the 2D divergence theorem, Gauss's divergence theorem that we just finished, right? So we've been down this road 5 times already. And this being number 6, I'm going to move a little more quickly since it's the same structure, basically all the same ideas with different details appropriate to the geometry. Okay, so here we go. We're going to be considering here a surface, what we call an oriented surface. To be clear, an oriented surface is a surface with what we call an orientation vector, right? Oriented surface, which we talked about before. Remember, if you have a solid 3-dimensional thing, the boundary is an oriented surface. So if you have an oriented surface, and this one perhaps has an edge to it, if it has a boundary curve itself, then we can reasonably ask which way should we orient the boundary curve itself? Should I think of this boundary as oriented that way, or should I think of this boundary as oriented that way? Right? So what's the deal? Why would I pick one versus the other? Well, we do have to make a choice. That choice is arbitrary. I guess you could say it was arbitrary 150 years ago, or I think we're pushing 200 now since this was first done. But the convention at this point is very standardized. So even though it is arbitrary, it is standard. It is not, optional. And the convention goes like this. It's a little bit harder to describe than previous ones we've talked about. But what you do is you start with the orientation on your surface, right? Like this. Keep in mind we begin with an oriented surface. You use your right hand, arbitrary, to be fair, but right hand, that's the deal. Thumb in the direction of your orientation vector for your surface. And then look at the direction that your fingers are kind of rotating, if you will. They're pointing to a direction that rotates around that thumb. And this is what I like to call a swirl. So your fingers define a swirl, like that. And now you just look and see how does that swirl as you kind of slide this whole thing closer and closer to the edge, closer and closer to this boundary that you're trying to orient. This swirl will sideswipe up against your boundary, and whatever direction of the sideswipe, that is the direction of the orientation on the boundary curve. So it's a pretty arbitrary rule, but it's a standard convention, and this is what everybody uses, so this is what we're using. And again, like I say, not optional. Does everybody see what the convention is?
Can you explain the side swipes one more time?
Yeah, so there's, let's see here. So the picture is a little hard to read, largely because I have these, let's see here. Why is that not? Okay, I don't know why that didn't work. Anyway, so on the surface, imagine that there's like just a little tempest, right? A little hurricane or something right there on the surface, and they could go around in one of two different directions. They can go like this, right, or they can go like that. Does that make sense? Yeah. So your thumb and your fingers are going to define which way that goes, and then as you drag. Let's see here. As you drag one of these swirls like this, as you drag it closer to the boundary edge, it's going this way. And then as you drag closer and closer, eventually you're going to see how it kind of hits up against. But as it hits the boundary, it's hitting going that way, not that way. Does that make sense? Yeah. Yeah. Sure. So that whichever way that side swipes up against the boundary, that's the induced orientation on the boundary curve. Arbitrary and kind of random. Okay. By the way, one thing. Oh yeah, question.
So we have to follow the normal though, right? Like if the normal is going down.
Yeah. That's the thing. That's right. So that's right. So we start with an oriented surface. Surfaces could be oriented which way. Who knows? Right? It's perfectly allowed for a surface to be oriented downward. So that's right. So you, whatever direction, let's say if it's oriented downward, then now look at my fingers. And they're going to be swirling the other way, and then it'll side swipe the other way. That's right. Okay, that's good. Okay, so that's the convention. All right, next, I claim boundary circulation accumulates. By the way, flashbacks to Green's theorem. When we were talking about Green's theorem, we were talking about a two-dimensional region with a boundary curve. Now we're talking about a two-dimensional surface with a boundary curve. Just like with Green's theorem, following the pattern, we're going to be looking at boundary circulation. So take your surface, look at the boundary, compute the circulation around that boundary. I claim that we're going to have an accumulating quantity. And the reason why is morally equivalent to what we saw in the Green's theorem context. That new edge that you get when you cut that surface into a second piece like this, well, as part of the boundary of this, will be oriented that way on that new edge. And as part of the boundary of this piece, normal fingers, swirls, it's going to be oriented like this on that purple edge. So this purple edge is going to show up twice. Opposite orientations, they cancel, they disappear, and we get accumulation just like with Green's theorem. Everybody cool with that? By the way, you may again, you notice these strong similarities with Green's theorem. A lot of people would point out, isn't this literally just Green's theorem? I mean, isn't that the same exact? I mean, we do the same exact things, and there's a case to be made there, depending on how you look at it. The distinction is that Green's theorem happens in the plane. It's a two-dimensional theorem. right, as typically thought of. And yes, this is kind of just a three-dimensional version of that, where we imagine sort of a surface instead of just a two-dimensional. We imagine maybe lifting that up into space. But it's still a two-dimensional thing with a one-dimensional curve, and boundary circulation is our accumulating quantity. And yeah, it's really, really similar. Okay. All right. So, accumulating quantity. Weird. Accumulating quantities have nice features. Again, I point out that you can think of accumulating quantities, such as boundary circulation, as behaving like stuff. Because, well, you know, as we just discussed, the boundary circulation of this hole is literally the sum of the boundary circulation on that piece plus the boundary circulation on that piece plus the boundary circulation on that piece plus etc., just like for any kind of a stuff. If you were talking about mass, the mass distributed across the green surface is the sum of the mass on that orange piece plus the mass on that purple piece plus the mass on that dark blue piece. Right? So it behaves just like stuff does. And as such, you can, and I would say should, think of it as a stuff. Because that's going to be really helpful for our purposes. Okay. All right. And with that noted, since it's like stuff, we can talk about its density. All right? So this right here, we're going to call that circulation density. Density, because it's what you multiply by size to get stuff, right? And circulation density specifically, because that's the stuff that we're talking about. So we've talked about mass density, because when the stuff is mass. We talked about population density when the stuff is population, right? So we're just following the linguistic pattern, circulation density. By the way, again, just like with Green's theorem. Okay, now where things do get different compared to Green's theorem, and this is a tough one, but the formula is different. And the reason that the formula is different is because it's a different setting, right? This is, in fact, a vector field in 3 dimensions. It is going to depend on how the surface is oriented. We're going to see better pictures of that coming up pretty soon, but the orientation of the surface will matter in terms of what your computed circulation density is. So there are some differences, but the interpretation is the same basic idea. And so when y'all see this coming up real soon, when we write down we put all the pieces together to make the theorem, that thing is just telling you circulation per unit area, namely its circulation density. Okay. All right, so let's put the pieces together. Excuse me. Y'all have seen something that looks like this, again, several times, right? So we have this formula that computes this thing called circulation. We're going to give that a name. Think of it as a kind of a quantity. We've observed that it's an accumulating quantity. The whole is the sum of the parts, like any other kind of stuff. Right? And stuff, as noted on the previous page, is stuff per unit size, namely density, times size. Right? And lo and behold, we have ourselves a theorem. Right? So this can be computed with that. If you want to compute a boundary circulation around the boundary of a surface in space, you could instead compute this surface integral over the surface whose boundary that curve is. How are we doing? Everybody all right? Okay. All right. So now y'all hopefully remember this little notational move right here. We've in the past find ourselves looking at orientation unit normal vector little n times ds scalar representing the area of a piece of surface. And in the past, we've abbreviated that as the ds vector. I think this is a really nice notation. I think it's really natural. I'm a fan. I like this a lot. Looks like the book agrees with me on this. And this is how I sort of, given my druthers, would prefer to write it, just because I think it kind of looks better on the page, if nothing else. Also, it's a little bit slightly fewer pencil strokes, right? So that's got to count for something. And this is how I write Stokes's curl theorem. How we doing? Everybody happy? All right, so let's use it. Let's do one. Y'all are probably going to recognize the pattern of this example. This is not exactly like our first example of Green's theorem, but it's really similar. So vector field given, parametrized curve given. The question is to compute this line integral. And again, of course, you could brute force this. You could take your parameterization and plug it in and do the pullback and all that whole mess. And you can see it coming. That'd be really annoying because x is trig, y is trig. All that plugs into here, and you'd have. It's not that it wouldn't be doable, but it's integrals we don't really want to mess with if we can avoid them. Okay, so what we're going to do, step one, we notice that we have been asked to compute a line integral. We notice that our brand new theorem involves computing a line integral. We are hoping that we can therefore use this theorem to compute that line integral that we're interested in. But there is a sticky wicket. The concern, just like with Green's theorem, just like with the divergence theorem, every other theorem we've seen before, the concern is this has to be a boundary, right? Very, very important for the theorem to hold is that this domain for our line integral that we want to compute with the theorem, that domain has to be a boundary of something. And so momentarily we're going to have to look at our curve that we've been given, this curve, this parameterized curve. We're going to have to check and make sure that it actually is a boundary. Now, before we do that, reminder, why? Do we need this to be a boundary? Well, if you look back at our development of this theorem, that's where we started. It started with the idea that we were looking at this accumulating quantity called boundary circulation. Everything hinged on it being a boundary. And if it isn't, then the whole thing comes crashing down like a house of cards. It just doesn't work. It doesn't make any sense. More immediately, visibly a problem. It has to be a boundary because whatever it is a boundary of is going to be the domain for our new flux integral. And so just to put it like really bluntly, if this curve here isn't a boundary of a surface, then there's no surface over which to even talk about this flux integral. So again, it's not that these two integrals are different, right? If this is not a boundary, it's that there is no second integral at all. Okay, so very, very important, and I make a huge deal, I get all dramatic and stuff about this every time we talk about this because I always see a certain number of students who kind of gloss over this, right? And who will take a line integral and just kind of start writing down flux integrals, but there is no flux integral. And the student, as they're writing it, might even be thinking, hey, I'm making progress, right? But they're writing stuff down that doesn't exist. It's not that the computation is wrong, it's that the computation makes no sense at all, right? It's just purely garbage. So please don't step on that landmine. It's very, very sad to see. And so I get as dramatic as I do about it because it's really, really important, and I don't want you all to step on that landmine. So tragic. All right. Okay, so let's go back to our question. We discussed that we need to establish whether or not our curve is a boundary. You all understand parametric curves, and this curve, parametrized like so, looks like this, and yeah, it's a boundary. Right? That's a boundary of, well, I actually have a bunch of different options, but the easiest one is it's a boundary of that disk right there. Is that cool? If you want to get weird with it for whatever reason, you could say, you know what, that's the boundary of the upper hemisphere. Right? The equator is the boundary of the upper hemisphere. That's also true, and if you want to use this surface, I guess you could. I don't know why you'd want to, right? It's just going to make life harder. But you do have options. You don't have to pick the obvious surface, but by and large, in the absence of a pretty compelling reason to the contrary, pick the easiest surface. And so, yes, I'm going to view it as this surface right there. Yeah.
It would give you the same answer if you did
Yep, absolutely. You get the same answer no matter which surface you pick, as long as the curve in question is the boundary of both of those surfaces. Right. By the way, let me just plant a thought. Something we're going to be talking about tomorrow. Wednesday, I'm pretty sure. You get the same answer no matter what surface you pick. That sounds like, you remember with path independence, you get the same answer no matter which curve you pick, as long as you have the same boundary points. Here, you get the same answer as long as you have the same boundary curve. So in the same way that we had this idea of path independence, we're going to find on Wednesday an analogous idea called surface independence. Yeah. All right. That's just foreshadowing. Okay. So now let's worry about orientations. Here's our surface. Oh, wait a minute. We need an oriented surface. All right, well, which way does this get oriented? And you just have to, there's two possibilities. Trial and error is your method to decide. Try one, see if it works. If it doesn't, try the other one. That's all it is. So if we oriented it up, right hand, thumb, think about the swirl, and just notice that would have us go in the wrong way. That doesn't work. Okay, let's try it going down. Right hand, thumb in the direction of the normal. Now we're experimenting with down. Now again, you look at the fingers of your right hand, and they are swirling around that way, which is the correct direction on our oriented curve. Does that make sense to everybody? Feel free. Questions? And there's you just have to play the game. You just have to do like this and just try your options. Think about which way the induced orientation works, and make sure that you pick the one that tracks with what you were given. This oriented curve is oriented like so, right? Flashbacks to many points earlier in the course, and so that means that we have to pick downward for our oriented surface. Okay, so we win. Our curve is a boundary. Because it's a boundary, we can write down Stokes' theorem. It's all over but the kind of the details at this point. And let's see here. You do have to compute the curl. So this great big vector field here, like that. You got to compute the curl. The curl, just algebra, right? But the curl ends up being 0, 0, 2. Make sure you can do that. I know it was a while ago that we wrote down the formula for curl back in chapter 3. So make sure you remember what that formula is. I strongly encourage that you remember it by way of the symbolic shorthand involving determinants and cross products, right? It's much easier to remember. Watch out for all the little potential minus sign oopses that can happen when you're doing determinants, right? That second term gets that little minus sign. So many students mess that up and will get wrong answers as a result. Anyway, there's the curl. As previously discussed, our normal vector for our new surface here is 0, 0, -1. That dot product is easy. The surface is barnyard variety. The integral drops in our lap and we win. Is that cool? What do you think? All right. Okay, so real quick, I think this is a nice perspective. I want to remind y'all real quick about this idea that I threw at you when we were doing the fundamental thermal line integrals. Remember, here's the first version of how we wrote down the fundamental thermal line integrals. After all, the big point was that change can be thought of as change per unit distance times distance, right? And with that in mind, we interpreted this thing, gradient dot t happened to be the thing, that we interpreted as change density because it's, again, stuff per unit size, stuff being changed, size being length. And having written it like that, we then observed that, okay, well, yeah, but you can do that. And that makes you want to ask, how should I interpret this equation? And with the idea being that dx is, I'm going to call it an oriented size, because its magnitude is literally the size. Its magnitude is ds. The magnitude is the size, but it also has a direction, namely the orientation, t. And so oriented size is pretty literally just telling you t ds. Okay. And with that noted, it makes sense to call the gradient itself an oriented density. And I know it's a weird concept to think of a density as having an orientation, but it actually tracks pretty nicely with our interpretation of gradient, because the gradient does have a magnitude and a direction. The magnitude tells you how steep is it, and the direction tells you, okay, well, I mean, uphill goes in various different directions, but nevertheless there is a single direction that is the real uphill, right? The direction where the altitude is increasing the fastest, right? So it's pretty natural to think of gradient as being both a magnitude representing how much the function's changing, and a direction telling you, yeah, but in which direction is that really happening? Okay, now, with that in mind, with that as a template, we're going to do all the same analogous observations here now about Stokes' theorem and curl. So here was our first version of Stokes' theorem, right? And I'm just to reproduce it. This is circulation per unit area. Circulation being circulation per unit area times area. So, as such, we call this circulation density, fine and dandy. We've already talked about that. All right, so here's where things get a little weird. We're going to combine our orientation and our size again. Right? N is the orientation, ds is the size. Put them together, reasonable to call this oriented size, if you will. Right? Just intuitively, hopefully believable. And then you look at this right here, and what is the thing? What do you think we should call the thing that you multiply by oriented size to get stuff? Well, I think oriented density is a reasonable thing to call it. And so that is, in fact, exactly what we're going to call it, what I'm going to call it anyway, oriented circulation density. The justification again, if you break it down as a vector and look at its magnitude and you look at its direction, this actually works really well because the magnitude of the curl does indeed tell us how much of a rotation is happening in the fluid. That's what the magnitude is, a scalar absolute measurement of how much the fluid is rotating in a general area. And the direction that it's pointing tells you around what axis is that circulation happening. And so just to go down here to the next page, you can see right away, given a curl, you can see, wrong color. That vector is going to point in a direction. The direction that it points, that's telling you whatever rotation the fluid is doing, this is the axis that rotation is actually sort of going around, right? And the magnitude, however long that curl vector is, that's telling you how much rotation is happening. Let's not get bogged down in stuff like units, right? But the longer the curl vector, the stronger the rotation. That's the basic idea. Okay. All right. So real quick, just to give you a kind of a plausibility check on this. Let's see. In fact, I think I can just do this like this. Yeah, let's do that. Okay, so here's a couple of scenarios. In fact, both of these are the same vector field, you're going to notice. This is just the same vector field drawn twice. And I want to think about how that vector field and looking at its resulting curl, again, notice that the vector field is rotating around the curl. Again, that's how curl works. And imagine a couple of different scenarios where we have a little piece of surface with boundary like this, and then we have another little piece of surface with boundary oriented like that. And does it track? Does it kind of make sense here? And I claim it totally does. Here's the fluid kind of rotating around. Notice the boundary is kind of rotating around kind of the same sort of way. So said differently, when the rotation of the fluid and the rotation, if you will, of the boundary, when that has the fluid literally following along and going around the same way that the boundary does, in other words, when you would pick up significant circulation, notice that the curl vector indicating what the fluid is rotating around, and the normal vector indicating what the, if you will, kind of the boundary is rotating around, those also line up. Right? So when the circulation lines up with the boundary that it's circulating around, then the curl lines up with the normal vector for that piece of surface. And so this dot product, curl dot in, large dot product corresponds to a large circulation. That doesn't prove anything, right? But that, I think, is at least satisfying that, okay, yeah, it should have worked out that way, right? And then analogously, you can look at where they kind of just don't line up. And so, for example, here, the vector field, same vector fields, this rotation of the fluid that way, it just doesn't line up right with this. It's one of these kind of situations, right? The rotation of the fluid and the rotation of the way that the boundary is going around, they're just around different. They're not going the same way. There's no circulation because the flow is not along the boundary. And that, again, tracks perfectly with the fact that the curl is not pointing in the same direction as the normal vector. So no circulation tracks with no dot product. Okay. All right, we're out of time, so we'll call it a day. See y'all on Wednesday. Picking up from here. See you later. Don't forget about attendance if I didn't already get you.